Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is Kirchhoff's current law. Our objective today is to develop an understanding of Kirchhoff's current law and use it to analyze electrical circuits. The simple statement of what goes in must come out belies the importance of such a seemingly no-duh observation. Given known inputs, one can easily calculate the output. If you poured a bushel of apples into a barrel, and your buddy poured another bushel of apples into the same barrel, you'd probably be surprised to see anything less or anything more than 2 bushels of apple in this barrel at the end of the day. Additionally, given known output, one can easily calculate the input. Let's say your lazy lab partner tags along for a day of apple picking. At the end of the day, your barrel has 2 bushels of apples and 1 vaguely apple-shaped rock in it. Given you and your friend picked a bushel of apples each, you are immediately aware your lab partner's contribution to this day-long effort is this single inedible rock. I leave it to you and the staff of the nearest emergency room to solve for how many vaguely apple-shaped rocks they may have ingested during the course of the day. The seemingly simple what goes in must come out observation is just as relevant and useful in circuit analysis if we think of electrons as tiny light blue apples. If a quantity of moving electrons enter a node, that same quantity of moving electrons must leave that same node. There may be numerous incoming or outgoing paths, but regardless, what goes in must come out. The German scientist Gustav Kirchhoff in the mid-1800s was the first to apply such a concept to electrical circuits. The simple statement of what goes in must come out is reworded in Kirchhoff's memorable observation that the algebraic summation of the currents entering and leaving a junction of a network is 0. It may help to rephrase this ever so slightly and state that for any given node, the sum of currents entering the node equals the sum of currents leaving the node. One side is reserved for incoming current, the other side reserved for outgoing current. What goes in must come out. The key concept is a junction, a node, or a region. One can define a node as a single point connection of many paths, or an amorphous blob encompassing a number of different internal or external connections. Regardless, what comes into this point or blob equals what comes out of it. Algebraic summation is just a $10 word that means pay attention to the direction of current entering or leaving a node. This is why I prefer the rephrased Kirchhoff's current law. For any given node, the sum of currents entering the node equals the sum of currents leaving the node. Pick one side of the equation to represent incoming current. The opposite side is reserved for outgoing current. What goes in must come out. Along the way, you might find a quantity of current with unknown direction, but with a little thought and effort, you should be able to manipulate your first draft to arrive at the answer you seek. I typically refer to Kirchhoff's current law by its initials, Kcl, and you'll often hear me refer to it as if it was a verb, as in the phrase Kcl it, meaning perform a detailed Kirchhoff's current law analysis and you will arrive at the answer you seek. In addition to it being used as an active verb, you can think of Kirchhoff's current law as exactly what the name implies, a law. If you break the law, you go to Kirchhoff jail. If the idea of pumping iron with a bunch of swarthy men and breaking rocks all day doesn't appeal to you, operate within the confines of Kcl and simply obey the law. Outside of a direct analysis technique, Kcl makes a great method of sanity checking your work to see if your results make sense. Those results outside the law are rounded up and punished or rehabbed accordingly. Keep in mind we'll be applying Kcl to very simple circuits in this lecture, but be aware that Kcl can be applied to even the most complicated of circuits. For any single node, the sum of incoming currents will always be equal to the sum of outgoing currents. Before we begin with the illustrated example portion of this lecture, I'm asking you to get involved, take part in the exercises, and really pay attention to this lecture. If I had to pick a single concept out of the entire Basic Electronics DC Circuit Analysis playlist that you simply cannot do without, it is Kcl. When we step into later scenarios involving analysis of complicated series parallel circuits, Kcl is the vorpal sword with which I leave a wake of vanquished foes. Quite like a sword, it is simple to use and extremely effective. Once you know which end to hold, the technique is to work yourself into a berserker-like rage and swing it forcefully, frequently, and wildly. We'll begin our discussion of KCl using this circuit consisting of two resistors in parallel with a single source. Let's review our basic properties of parallel circuits and spend some time discussing current distribution within this circuit using Ohm's law. The first and most basic property of parallel circuits is that voltage across elements hooked in parallel is the same. Therefore, it can be said that E, our generic supply voltage, is equal to the voltage across resistor 1, V1, and also equal to the voltage across R2, V2. E equals V1 equals V2. The current through resistor 1 is the voltage across it divided by its resistance. I1 equals V1 divided by R1, and the current through resistor 2 is the voltage across it divided by its resistance. I2 equals V2 divided by R2. We could solve for source current using Ohm's law, though as you'll see this is not my preferred means of doing so. Using this method, source current IS is equal to the supply voltage E divided by total resistance RT, where total resistance is the parallel combination of those resistances in this path. RT is R1 in parallel with R2. This is the reason I do not prefer this method. It requires a calculation step not readily solvable in your head. Regardless, if one was to idealize this two resistor parallel combination as a single resistance RT, it is readily apparent that the current through it is obviously equal in magnitude to the source current IS. It stands to conjecture that R1 and R2, those resistors that compose RT, draw representative portions of this source current, no more, no less. It can be said, therefore, that IS equals I1 plus I2. We can go any number of rounds with Ohm's law and perform any derivation you wish, but the easiest method I've found to convey this simple fact is this. Return to our original parallel circuit and ask yourself these questions. Where did I1 come from? Where did I2 come from? The answer in both cases should be the source. If the source delivers both I1 and I2 to this parallel combination, it is quite obviously the source of I1 plus I2. Do not make this hard. My advice is to look at circuits from the perspective of flowing current and ask where current came from, where it's going to, and whether it has a choice of paths. Again, I cannot express how critical this step is to performing series parallel circuit analysis as we progress through this playlist. This technique is visual, reliable, and powerful. Current through elements in series is the same. Voltage across elements in parallel is the same. KCl is the method you use to determine if elements are in series or in parallel with one another. The point is, you don't need to solve for things you already know via basic circuit properties. Returning to this parallel circuit, if a given quantity of conventional current leaves the positive terminal of the source, it has no choice but to travel from the positive terminal to this amorphous blob I'm calling node A. That same quantity of current must leave node A. However, it has a choice to travel through two paths, either through R1 or through R2. Given that resistance is defined to be the measurable opposition to current, one can expect a larger amount of this incoming current to travel through the path presenting the least opposition, and a smaller amount of this incoming current to travel through the path presenting the most opposition. Current should flow through paths inversely proportional to their resistance. We'll return to this statement in a later lecture using a shortcut called the current divider rule. Regardless of the division of outgoing current between these two paths, all incoming current must leave, no more, no less. IS must equal I1 plus I2. Realize this is not the only node in our circuit upon which we can apply KCl. Consider what happens at node B. Here's where again a visual analysis of this circuit from the perspective of flowing current shortcuts us straight to KCl. As I1 travels through R1 and I2 travels through R2, it has no choice but to recombine at node B, where we are again left with a realization that I1 and I2, our incoming currents, must equal IS, our outgoing current. I1 plus I2 equals IS. Alright, we've done a sufficient general orientation of this circuit. Let's just put some numbers in here and use KCl and Ohm's law to solve for source current Is and the current through each element I1 and I2. Our source voltage is 48 volts. R1 is a 750 ohm resistor. R2 is a 910 ohm resistor. Given I1 equals V1 divided by R1, substituting in the necessary values, we find I1 to be approximately 64 milliamperes. Given I2 equals V2 divided by R2, substituting in the necessary values, we find I2 to be approximately 52.7 milliamperes. Given our earlier Kcl analysis of this circuit, we can use the understanding that Is equals I1 plus I2. Substituting in the necessary values, we find Is to be approximately 116.7 milliamperes. Compare and contrast the ease and simplicity of solving for source current using Kcl with that of performing total resistance calculations, and an additional statement of Ohm's law. Not only does Kcl solve for source current in a single step, it does so using simple addition rather than a cumbersome formula. If one still desired to solve for total resistance, one could easily use a restatement of Ohm's law, where resistance equals voltage divided by current. Substituting in the necessary values, we find RT to be approximately 411.1 ohms. If you are suspicious of such an easily obtained value, you can check your work and solve for RT using your choice of the parallel resistance formulas. Both steps yield the same result, and we can be reasonably certain our analysis is correct. That's the point of Kcl. Not only is it a handy shortcut that can be used as a substitute for Ohm's law, it can be used to check Ohm's law. And, wrapping back to previously covered material, Ohm's law can be used to check Kcl. The important point is that both methods should agree, and they should both be correct. If at any point we incorrectly performed any step, our Kcl analysis wouldn't work out, and we could track down the source of our problems and rectify or rehab those results that need it. Let's say, for example, we totally dorked up an early step of this problem and just transposed the 9 and the 1 and the 910 ohm resistor, and you accidentally punch 190 into your calculator. Don't laugh, it happens. Using this incorrect resistance, we would anticipate I2 to be approximately 252.6 milliamperes, but it isn't. Your first clue that something is awry should be that a 910 ohm resistor, the largest resistance in this parallel combination, is drawing substantially more current than the 750 ohm resistor with the same voltage across it. Let's say though you spent the night in an ER waiting room and you're a little spent, so this fact goes unnoticed at first. Using the two parallel resistor formula, you solve for parallel resistance of this combination to be approximately 411.1 ohms, and then use Ohm's law to solve for source current, where source current Is is equal to E divided by RT, and anticipate it to be approximately 116.7 milliamperes. However, aware you are not at your bright-eyed and bushiest, you take the wise precaution of checking your work using Kcl. Using your understanding that Is equals I1 plus I2, your initial Kcl analysis suggests that 64 plus 252.6 equals 116.7, but it doesn't, and you are now keenly aware of this fact and can go back and trace down the source of your troubles. In this case, an incorrect Ohm's law calculation because of the transposed digits. Again, there are numerous opportunities to check your work. Treat everything with mistrust and suspicion until amply verified. Beyond its ability to be used as a substitute or check to Ohm's law, one of the greatest and most powerful applications of Kcl is its use in real-world measurement and troubleshooting scenarios, without having to solve for voltage, without having to solve for total resistance or any other make-work stumbling blocks, with a known current input and a single current measurement through either element in a two-element parallel network. You instantly and reliably know the current through the other element using a simple restatement of Kcl. Calculations aside, if you took your DMM in DC ammeter mode and measured the source current to be 116.7 milliamperes and took another current reading through the first resistor Even if the resistance value is unknown and the resistor color code somehow obscured or unreadable to be 64 milliamperes, you could be reasonably certain that the remaining 52.7 milliamperes is traveling through the second resistor, given our restatement of Kcl as Is minus I1 equals I2. Having observed Is at 116.7 milliamperes and I1 at 64 milliamperes, solving for I2, we find it to be 52.7 milliamperes as expected, without taking a third current measurement using the ammeter. That's the point. Kirchhoff's current law saves you time. Consider Kcl applied to this configuration of conductors. No resistances or voltages or any other obfuscations are distracting us from the true heart of Kcl. It is the checks and balances of moving objects inside pipes. If pipe A is applying 3 amps of current in the indicated direction, pipe B is applying 1 amp of current in the indicated direction, and 5 amps of current is pouring out of pipe E, what is the current magnitude and direction inside the other pipes? By all means, pause the lecture and take a shot at this. Kcl calculations are trivial addition and subtraction problems only, and this example requires absolutely no knowledge of electrical theory other than a basic understanding of what goes in must come out. At this junction, pipe A and pipe B are supplying respectively 3 amps and 1 amp of current into pipe C for a total of 4 amps. If 5 amps of current is pouring out of pipe E, it must mean that an additional 1 amp of current is being input via pipe D. It makes sense. You can draw an amorphous blob around the whole collection of conductors where the current through pipe C is negligible, or one could use an amorphous blob to visualize pipe C as a single input, which in actuality is the summation of 2 inputs, A and B. We'll return to this visualization in a moment after we play around with this example a little bit. There is nothing to distract us from the essence of Kcl, and it's probably a welcome relief from some of the daunting challenges I've thrown at you already. Take advantage of this break while you can, though, because more challenges lie ahead. Let's say pipe A is now supplying 80 milliamperes of current in the indicated direction. 60 milliamperes of current is traveling down pipe C in the indicated direction, and 15 milliamperes of current is coming out of pipe D. What is the current magnitude and direction inside the other pipes? By all means, pause the lecture and take a shot at this. At this junction, 80 milliamperes of current enters via pipe A, and 60 milliamperes leaves via pipe C. Current of unknown magnitude and direction is inside pipe B. I know the answer is readily obvious, but allow me to make this important point. You can make incorrect initial assumptions about unknown current direction and still get a right answer. That's the beauty about Kcl. As long as you're consistent and account for all incoming and outgoing current, you can be totally wrong and call incoming current outgoing and vice versa, and still get a right answer. Let this be small comfort to those individuals that are consistently wrong. Even stop clocks get the time right twice a day. Let's assume that the current in pipe B is incoming current. Our Kcl equation for this junction is as follows. Our incoming current is IA plus IB, and our outgoing current is IC. IA plus IB equals IC. Substituting in the necessary values and solving for IB, we find IB to be negative 20 milliamperes, meaning our magnitude is correct, but our assumed direction is incorrect. 20 milliamperes is in fact leaving this junction. It makes sense. If 80 milliamperes enters via door A and 60 milliamperes leaves via door C, the remaining 20 milliamperes has to leave via the only other door at this junction, door B. If we revisit Kcl at this junction and assume IB is leaving the junction, our Kcl equation for this junction is IA, our input, equals IB plus IC, our outputs. IA equals IB plus IC. Substituting in the necessary values and solving for IB, we find IB to be 20 milliamperes as we expected with the correct assumed direction. Moving on to the other junction and assuming our unknown current IE is leaving the junction, Our Kcl analysis suggests that incoming current IC equals the summation of our two outgoing currents, ID plus IE. Our Kcl equation for this junction is IC equals ID plus IE. Substituting in the necessary values and solving for IE, we find IE to be 45 milliamperes. Our initially assumed direction of outgoing current is correct because we found this current to be positive in magnitude. Given that last illustrated example problem featured only current and did not include any resistors or sources or any other devious mathematical trickery besides basic addition, subtraction, and algebraic manipulation, step back for a moment and ask yourself if this circuit is in any way, shape, or form different, and is Kcl any harder to apply? No, it's a simple checks and balances of moving current. If source current is known to be 80 milliamperes, and we observe 60 milliamperes of current in the conductor leading to both R2 and R3, what is the current through R1? It is quite obviously the remaining 20 milliamperes. Additionally, knowing current delivered to both R2 and R3 to be 60 milliamperes, and knowing current through R2 to be 15 milliamperes, it is quite obvious that the remaining 45 milliamperes must go through R3. There is absolutely no difference between this illustrated example problem and our previous illustrated example problem, with this one minor exception. Solve for voltage across these resistors and solve for the resistance values of the unknown resistors R2 and R3, given that R1 is known to be 450 ohms. Here's where your knowledge of basic parallel properties, Ohm's law, and spatial awareness comes into play. Voltage across elements in parallel is the same. Resistance is voltage divided by current. The toughest part of this whole problem for some people is not electrical in nature, but rather the physical arrangement of these three resistors. They are all in parallel with one another. I simply cannot stress the importance of voluminous practice and repetitive exposure if this is not readily evident up front. These resistors are in parallel with one another because they are all two-terminal components with one of their two terminals hooked to the same point. This amorphous blob I'm calling node A. Yes, within node A, there is a subdivision, but all three paths originate at this single point. This is like a single highway entering a city, and current bound for R1 takes the first exit. Current bound for R2 and R3 travels to the next fork in the road, and then makes the appropriate turn. This is not the only way three resistors can be arranged in parallel. R1 and R2 and R3 can be arranged in this manner. I like to think of this as a single highway that instantaneously splits into three exits. Current bound for R1 takes the left-hand lane. Current bound for R2 stays center. Current bound for R3 takes the right-hand lane. If this was New Jersey, current would have to stop every half mile at a toll booth and honk and swear frequently. Here's another equally valid arrangement of three resistors in parallel. I like to think of this as a single trunk road off of which there are turns to the intended destination. Current bound for R1 takes the first right turn. Current intended for both R2 and R3 continues on as previously. Current bound for R2 takes the second right turn. Current bound for R3 continues on to the last turn on the right next to the barking dog and the BFT. What's interesting to note is that the arrangement of resistors does not matter. You can group R1 and R3 together and put R2 on the far right. Now incoming current splits into two paths. The first path being the current intended for both R1 and R3. The second path being that intended for R2. The first path is then again subdivided between R1 and R3. You are only limited by your creativity in arrangement, rearrangement, redrawing, and simplification of parallel networks. Regardless the arrangement of exits, overpasses, turns, roundabouts, and jug handles, all incoming current must travel the single highway into this node, and all incoming current must leave it. More current will travel through paths with less opposition. Less current will travel through paths with more opposition. Equally relevant is the rejoining of individual paths at the bottom node. Regardless of the physical configuration, any parallel circuit of three resistors yields the same Kcl equation. Incoming current is I1 plus I2 plus I3, and outgoing current is Is. Returning to our original problem statement, we've been asked to solve for the voltage across each resistor and the resistance of the unknown resistors R2 and R3. By all means, pause the lecture and take a shot at this. It should not be new material, but rather a synthesis of basic parallel properties, Ohm's law, and our newfound appreciation of Kcl. Since these resistors are in parallel with one another, the voltage across them is the same. V1 equals V2 equals V3. Given we know both the current through and the resistance of R1, it is very easy to solve for the voltage drop across it. Where V1 equals I1 times R1, substituting in the necessary values, we find V1 to be 9 volts. Given the most fundamental property of parallel circuits, it can be said, no calculations needed, that both V2 and V3 are also 9 volts. Given we know current through and voltage across both paths, we can use our understanding of Ohm's law to solve for the resistance of each path. Where R2 equals V2 divided by I2, substituting in the necessary values, we find R2 to be 600 ohms. R3 is V3 divided by I3. Substituting in the necessary values, we find our unknown resistor R3 to be 200 ohms. What is interesting to note is that the various simplifications that can be made of this 3-resistor parallel network. For example, one could combine R2 and R3 in parallel to make an imaginary resistor R' and place this in parallel with R1. What is the current drawn by R' with 9 volts across it? If R' is R2 in parallel with R3, the 2-resistor parallel formula says R2 in parallel with R3 is a 150 ohm resistor. With 9 volts across a 150 ohm resistor, Ohm's law states that IR' equals VR' divided by R'. Substituting in the necessary values, we find IR' to be 60 milliamperes, exactly what the setup for our original Kcl told us without the necessity of solving for parallel resistance. IR' is the current drawn by both those resistors that make up R', notably R2 and R3. It can be stated that IR' equals I2 plus I3. The highway visualization makes this readily apparent and does not require goofy calculations. Basic addition and subtraction is easy. Kcl is easy because it is at its very core basic addition and subtraction. Let's do a quick test. How much would R double prime, the imaginary parallel combination of R1 and R3, draw with 9 volts across it? Those with an understanding of Kcl can quickly add the current drawn by both R1 and R3 to yield the result of 65 milliamperes. Those sleepwalking zombies relying upon resistance calculations need to solve for R double prime, the parallel combination of R1 and R3, to be approximately 138.5 ohms, then an additional Ohm's law calculation to yield the same result of 65 milliamperes. This is exactly what we came up with using the quick and easy Kcl equation and our revisualization of our parallel circuit as a highway, in this case having a single exit ramp servicing both R1 and R3. This is the tremendous advantage of Kcl in contrast to some of the previously discussed circuit analysis properties, and why it is my weapon of choice. It is both visual and self-evident. Redraw the circuit in any fashion you see fit, and just stay organized. The math should be trivial, and importantly, the math will save you time. Allow me to demonstrate. Here's another parallel combination of 3 resistors. Incoming current is known to be 15 milliamperes. Current through one of the resistors, R1, is known to be 4 milliamperes. Given R1 equals 4.5 kiloohms, R2 equals 3 kiloohms, and R3 equals 3.6 kiloohms, solve for the current through the remaining resistors, I2 and I3. Pause the lecture and take a shot at this. How can basic parallel properties be used to your advantage? And importantly, how can Kcl be used to save you time? Resist the zombie-like urge to shamble into this circuit analysis by solving for parallel resistance. You do not need to, and it will only waste your time. If the incoming source current splits between three paths, our Kcl analysis suggests Is equals I1 plus I2 plus I3. Substituting in the necessary values and solving for the unknown quantities I2 plus I3, we find I2 plus I3 to be the remaining 11 milliamperes. It may help you to visualize this circuit as such. 15 milliamperes of source current enters here. 4 milliamperes of it goes through R1, and only 11 milliamperes travels on to both R2 and R3. Stop right here. Those individuals that know and understand the current divider rule shortcut can solve for the unknown currents in one step. You'll understand and appreciate this shortcut when we discuss it in a later lecture. Most importantly, the quick and easy Kcl analysis got us directly to the point where we could apply the current divider rule shortcut using only basic addition and subtraction. We'll discuss the current divider rule in a later lecture. Remember this step though. Kcl routes us directly to a shortcut. For now, we're left with the tools we have, notably basic parallel properties, Ohm's law, and Kcl. Let's apply the most fundamental of parallel properties. Voltage across elements in parallel is the same. V1 equals V2 equals V3. Using Ohm's law, we can solve for V1, where V1 equals I1 times R1. Substituting in the necessary values, we find V1 to be 18 volts. It can be said, no calculations needed, that both V2 and V3 equal 18 volts. Using another iteration of Ohm's law, we can solve for either I2 or I3. Let's randomly choose to solve for I2 first, where I2 equals V2 divided by R2. Substituting in the necessary values, we find I2 to be 6 milliamperes. We could use another iteration of Ohm's law to solve for I3, but that would be exceedingly zombie-like to do, since we've got our choice of two Kcl equations that are far easier to manipulate than even Ohm's law. First, we could step all the way back to our initial Kcl analysis equation that states Is equals I1 plus I2 plus I3. Having been given both Is and I1, and having solved for I2 using basic parallel properties in Ohm's law, we can substitute these values into the equation and solve for I3, where we find I3 to be 5 milliamperes. Alternately, we can use our second Kcl analysis, looking at just I2 and I3, where I2 plus I3 equals 11 milliamperes. This is the lump sum of current that is traveling just to R2 and R3, with that amount of source current destined for R1 having been removed from consideration. Again, it may help to visualize this Kcl equation using an alternate depiction of the same parallel circuit. Having solved for I2 using Ohm's law, we can substitute this into this second Kcl equation, and again solve for I3, where I3 is the remaining 5 milliamperes. Notice at no time did the application of Kcl necessitate me solving for parallel resistance, nor did it require me doing a bunch of Ohm's law calculations when simple addition, subtraction, and basic algebraic manipulations yielded the same results. Check my work if you don't believe me, but realize the more time you spend doing parallel resistance calculations in Ohm's law is less time you have to do radical things like skateboarding or paragliding. One more illustrated example problem before we conclude this lecture, this time one featuring a potentiometer. Given this circuit, see if you can determine the setting on the potentiometer such that the 12-volt source is continually delivering 360 milliwatts of power to the entire system. The system being defined as that power dissipated by the two resistors, the fixed resistor RF at 3 kiloohms and the adjustable potentiometer, RP. Pause the lecture and take a shot at this. See if you can use your understanding of the power equations, basic parallel circuit properties, and your newfound appreciation of Kcl to come up with a desired answer. Struggle with it, and don't just sit there like a houseplant waiting for me to do the work for you. If you are struggling, here's a hint. What is the current requirement for a 12-volt source delivering 360 milliwatts? And does the current through the fixed 3 kiloohm resistor ever change? What this illustrated example problem is basically asking you to do is to adjust the potentiometer such that the current supplied by the 12-volt source delivers 360 milliwatts to these two resistors. What is the current requirement for a 12-volt source delivering 360 milliwatts? If power is voltage times current, a rearrangement of the power equation yields current equals power divided by voltage. Substituting in the necessary values, we find source current must equal 30 milliamperes. What constitutes source current? A Kcl analysis of this circuit suggests that source current equals the current through the fixed resistor, IF, plus current through the adjustable potentiometer, IP. IS equals IF plus IP. Given this is a parallel combination of resistors, voltage across them is the same. VF equals VP, and they both equal 12 volts. The fixed resistor RF, regardless of the setting on the adjustable potentiometer, will draw a measurable portion of source current, where this portion IF is VF divided by RF. We find the fixed 3 kilo ohm resistor will continually draw 4 milliamperes of the incoming 30 milliamperes. Where must the rest of the incoming current go? Obviously, the remaining current must travel through our adjustable potentiometer. Given IS equals IF plus IP, and substituting the necessary values, we find that the current drawn by the adjustable potentiometer to be 26 milliamperes. Using Ohm's law to solve for the resistance of the adjustable potentiometer, we find Rp equals Vp divided by Ip. Substituting in the necessary values, we find the potentiometer must be adjusted to approximately 461.5 ohms to draw the required amount of current. Given the fixed resistor is drawing 4 milliamperes and the adjustable potentiometer drawing 26 milliamperes, it can be said that the source is supplying 4 plus 26, or 30 milliamperes of current to the whole system, and thus delivering the required 360 milliwatts of power. The key to the resolution of this problem is the understanding that what goes in must come out, and what comes out must necessarily have come in. Before we bring this lecture to a close, pause to consider a subtle modification of this last problem into a series parallel circuit. This is where your understanding of basic series and basic parallel properties, and both Kirchhoff's voltage and Kirchhoff's current law, pays major dividends. I've taken our 3 kilo ohm fixed resistor and divided it into two resistors, R1 being a 1 kilo ohm resistor and R2 being a 2 kilo ohm resistor. The resistance of this left-hand parallel path is still 3 kilo ohms from end to end, and there is still 12 volts across it. Additionally, I've taken our 461.5 ohm potentiometer and divided it into two resistors, R3 being 200 ohms, and R4 being the remaining 261.5 ohms. The resistance of this right-hand path is still 461.5 ohms from end to end, and there is still 12 volts across it. Have I in any way, shape, or form changed this circuit? The answer is no. With 12 volts across a 3 kilo ohm path, it will still draw 4 milliamperes of current from the source. With 12 volts across a 461.5 ohm path, it will still draw 26 milliamperes of current from the source. When two paths are drawing respectively 4 milliamperes and 26 milliamperes of current from the source will supply 4 plus 26, or 30 milliamperes of current. Here is where things get interesting. Look at Kirchhoff's current law. What is the current through R1 with respect to that of R2? It is the same. I1 equals I2, and they both equal 4 milliamperes. What is the current through R3 with respect to that of R4? It is the same. I3 equals I4, and they both equal 26 milliamperes. Now let's look closely at the voltage drop across individual resistors inside the parallel paths. Ohm's law states that the voltage drop across a resistor is the current through it times its resistance. V1 equals I1 times R1. Substituting the necessary values, we find V1 to be 4 volts. V2 is I2 times R2. Substituting in the necessary values, we find V2 to be 8 volts. Now let's apply Kirchhoff's voltage law to this loop, including just the left-hand parallel path. The sum of rises equals the sum of drops. E equals V1 plus V2. Substituting in the given and calculated values, we find V1 plus V2 does in fact equal the voltage supplied to this path. Now apply Kirchhoff's voltage law to this loop, including the right-hand parallel path, and take advantage of this fact. The sum of rises equals the sum of drops. E equals V3 plus V4. Using Ohm's law to solve for V3, we find V3 equals I3 times R3. Substituting in the necessary values, we find V3 to be 5.2 volts. Substituting this calculated value into our second KVL equation and our given supply voltage, and solving for V4, we find V4 to be 6.8 volts without using Ohm's law. If you want to check your work using Ohm's law, that option is available, and if you have time to do so, it is a recommended practice. Where V4 equals I4 times R4, substituting in the necessary values, we again find V4 to be 6.8 volts. Notice at no time did I introduce any new subject material, nor did I perform purposeless calculations, nor employ alternate circuit analysis methodologies with funny names. The point of this diversion is this: don't solve for stuff you don't have to. You don't need to solve for the current through elements hooked in series because current through elements hooked in series is the same. You don't need to solve for voltage across elements hooked in parallel because voltage across elements hooked in parallel is the same. What goes up must come down regardless of which loop you travel, and what goes in must come out regardless of which node you look at. KVL and Kcl are easy and visual means smart and efficient folks use to determine what elements are in series or in parallel with one another, and then use these facts to cut straight to the heart of the matter quickly and efficiently, then spend the rest of the day hanging out and looking cool. Sleepwalking zombies just bang up against these easily surmountable walls, never once realizing there's a door you can walk straight through. We'll return to these properties applied to more series parallel circuits in the very, very near future. But for now, file it away as a very important point. In conclusion, this lecture took a look at Kirchhoff's current law and used it to analyze simple circuits. I will be so bold to say that Kirchhoff's current law is the most single useful circuit analysis technique I can teach you. It is visual, reliable, efficient, and effective, and we will be applying it on a regular basis from this point forward. Remember to review this concept as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.